Pramod Gopinath, Director of the International School of Photonics, to formally invite this speaker. Pramod sir, over to you.
Thank you, Dr. Praveen. Good morning, Professor Robert Boyd, and good evening to others who have joined from the Indian subcontinent. Professor Robert Boyd is the Canada Excellence Research Chair in Quantum Nonlinear Optics and Professor of Physics at the University of Ottawa. He received his bachelor's degree in physics from the Massachusetts Institute of Technology and holds a PhD in physics from the University of California at Berkeley. In 1977, Professor Boyd joined the faculty of University of Rochester, and in 2001, he became the M. Parker Givens Professor of Optics and Professor of Physics. His research interests include studies of slow and fast light propagation, quantum imaging techniques, nonlinear optical interaction, studies of nonlinear optical properties of materials, nanofabrication, plasmonics, and the development of photonic devices, including photonic biosensors. Professor Boyd has written 2 books, co-edited 2 anthologies, published nearly 500 research papers, and been awarded 10 patents. He is a member of the Heidelberg Academy and of the Royal Society of Canada. He is a past winner of the Towns Award, Shallow Prize, and Humboldt Research Award. He is a fellow of the IEEE, Optical Society of America, American Physical Society, and the SPIE. Professor Boyd has served as a member of the Board of Editors of Physical Review Letters and is currently a member of the Board of Reviewing Editors of Science Magazine. With these words, let me welcome Professor Robert Boyd to International School of Photonics at Kochi University of Science and Technology to deliver the Silver Jubilee Lecture. Over to you, Professor.
So, Professor Gopinath, thank you very much for that very kind introduction. When you say all those things, it doesn't even remind me. It doesn't even remind me of myself. But thank you for your kind words. Okay, so I'm going to talk about how light behaves when the refractive index vanishes, and well, as the talk goes on, you'll see why this topic is really so fascinating. I have faculty positions both at Ottawa and at Rochester. And let me call this to your attention. I always post the visuals of my talk. So if anybody wants to look back at something that I showed today, it is there for you to take a look at. Okay, here's a very, very brief outline of the talk I'm going to give. First, I'm going to talk about epsilon near zero and near zero index materials, and talk about the physics of how light behaves in this situation. I'll then move specifically to the nonlinear optical properties of these epsilon near zero materials. Talk briefly about how metamaterials can be developed to show these effects. And then at the end, I'll show you some applications of zero index materials that my colleagues and I are working on. Okay, so don't worry, I'm not going to go through this word by word, but let me just motivate why it is that I'm interested in the nonlinear response of ENZ materials. So first of all, we know that nonlinear optics, I like to say nonlinear optics is good. There are a lot of applications that come out of nonlinear optics, and at a formal level, there's a fundamental understanding of light-matter interactions that comes from nonlinear optics that one would never realize from just linear optics. Okay, so even though nonlinear optics is technologically important, the nonlinear response is usually much weaker than the linear response. So over the decades of research in nonlinear optics, people have looked for means to enhance the nonlinear response. They've looked at resonance interactions. They've looked at plasmonic systems, at electromagnetically induced transparency, and at metamaterials. Now, the approach that I am following right now is to use epsilon near zero materials, either natural materials or metamaterials. And let me now explain why epsilon near zero materials are so intriguing. So first of all, well, we know that the wavelength of light in a material system is the vacuum wavelength divided by the refractive index. So if the refractive index is nearly zero, the wavelength is significantly lengthened. Well, we also know that the phase velocity of light is given by c over the refractive index. If the refractive index vanishes, then the phase velocity of light will approach infinity. So these two properties taken together tell you that as n approaches zero, the field oscillates in time, but not in space. The oscillations are in phase everywhere. So these properties are entirely consistent with Maxwell's equations, with the wave equation, but we're operating at a limit that's quite unusual, that the field oscillates in time, but it's uniform in space. And these ideas have gone back to 1953, although really the big push on this has been the work of Nader and Gaeta, who really got people excited about epsilon near zero materials. So I'm not going to go through this for the physics. I just mainly want to establish some notation. We know that the dielectric, the dielectric permittivity, also known as dielectric constant, is defined through this equation here. So epsilon zero is the permittivity of free space. Epsilon, in my notation, epsilon will be the relative permittivity. We could also define a magnetic permeability through the analogous relation relating the H field, the B field to the H field. And now, as probably everyone in this room has done many times, we know that the refractive index is given by the square root of epsilon times mu. So we can get a zero index material either by having epsilon vanish or having mu vanish or having both of them vanish. So it's usually important. So throughout the talk, I'll try to be careful to tell you whether I'm talking about ENZ, MNZ, or EMNZ. Epsilon and mu near zero. So why do we care? It seems as if I've been making this distinction between epsilon near zero and epsilon and mu near zero. Why do people care? Well, there's the problem of surface reflection. We know that at any interface between two materials, there's going to be a reflection of the light. And the reflection, the surface reflection, the intensity reflection can be written in this form here, where Z is the impedance of the interface, and it's given by the square root of mu over epsilon. And now, look, if epsilon is zero and mu is anything other than zero, then Z is going to diverge and the reflectivity is 100%. So, so you just can't get light into the material if you have this ideal situation in which epsilon is equal to zero. So you need both epsilon to be zero and mu to be zero, and you want the ratio of the two to be finite, and that is the way that you can get light into the material. Now, I should say that this is a really idealized situation. In most of my own experimental work, we do not have epsilon small enough to worry about these things. But the harder you work at getting epsilon small, the harder you also have to work to get mu small. And it's not easy to get epsilon small, but it's even harder to get mu small. Okay, so let me tell you about some of the physical processes that occur in epsilon near zero materials. First of all, there's a modification of fundamental radiative processes. And I'm thinking now of the Einstein A coefficient and the Einstein B coefficient. Of course, Einstein derived these relations for an atom in vacuum, but it's reasonably straightforward. And my friend Peter Maloney is one of the people who's done this. It's reasonably straightforward to repeat Einstein's calculation, but for an atom embedded in a dielectric material. And here's what you find is that the Einstein A coefficient is given by the usual A coefficient for an atom in vacuum times the refractive index. Now, if we have if we have the refractive index vanishing, it means that the spontaneous emission rate vanishes. It means we can turn off spontaneous emission. That has some implications I'll get to in a second. We have the Einstein B coefficient. This is the one that allows us to calculate the stimulated emission rate. And we find that the B coefficient is the vacuum B coefficient divided by the refractive index times the group index. So as n becomes small, we find that the optical gain becomes very large. So what are some of the implications of this? Well, first of all, if we can inhibit spontaneous emission, we can build thresholdless lasers. All lasers have a certain threshold. You have to pump them hard enough to even get any gain at all. Why is that? Well, because spontaneous emission is a loss mechanism. When you try to pump a laser, if you want the light to you want the excited atoms to amplify an optical field, you don't want them to decay spontaneously. So that's one example. In others, we expect super radiance effects to be pronounced in these ENZ materials. I guess just for the simple reason that if the field is everywhere in phase within the material, then you automatically have cooperative emission. I mean, every atom is radiating phase with the other atoms. And both of these are processes that people are working on right now. No complete experimental demonstration of these two effects, but people are working very hard at demonstrating them. So now let's turn to the optics of zero index material. And even at the level of Snell's law, we find that there's some very, very intriguing effects. Let's see what happens when a ray of light falls on the interface between a zero index material and air or vacuum. What we find is that independent of the angle of incidence on this side, the light always leaves perpendicular to the surface. It's just a simple manifestation of Snell's law. Now, by the reversibility of light waves, this also tells you that light can enter an ENZ material only at normal incidence. So if here's a ray of light falling onto the zero index material, and you find that for any angle of incidence other than the normal incidence, you will have 100% reflectivity. Now, what if you do come in normal to the what if you do come in normal to the interface? Well, then any angle theta inside will satisfy Snell's law. So how does nature know what to do? Well, you just can't use ray optics to describe this sort of situation. You have to use wave optics. So my colleague Orad Reshev has done a full wave simulation of what's going on. Here's a beam of light falling onto a zero index material. And here are the phase fronts of the light leaving the material. So indeed, light is emitted in all directions, as one might have guessed, just by the basis of Snell's law. Now, just very quickly, some other consequences of epsilon near zero. I'll call these funny lenses. No matter how light gets into this zero index material, it always leaves the rays perpendicular to the surface. So the wave fronts will be plane waves. If you put a curvature on the surface, you find that the light leaving the material will be a spherical wave converging on this point right here. Other implication is that you can build large area, single transverse mode surface emitting lasers. When you're building a surface emitting laser, there's usually a limit to how large these dimensions can be. Well, you want the dimensions to be as large as possible because you can generate more power from the laser if these dimensions are large. Usually you need these dimensions to be much smaller than the wavelength of light. But in a zero index material, the wavelength becomes infinite and you can make this the size as large as you want. And I'll just point out that there is no Fabry-Perot fringes. As a beam of light passes through this material, there's no interference effects because the beam does not pick up any phase shift in traveling from the entering surface to the exiting surface. And I have references here. These effects have all been observed. Other one is super coupling of waveguides. Imagine here just a normal waveguide. Here's another normal waveguide. You want to couple light so that the light leaving this waveguide, all of it enters this waveguide. Usually this is very difficult. You go in the laboratory and you get micro positioners and you have to get all the angles just right. But there's a simpler way of doing it. Here you have a region of any geometrical shape. It's a zero index material. You put a metal cladding on it, except for the entrance port and the exit port. Any light entering here has to leave by this port here. Coupling between two distant waveguides. You know, if you build a directional coupler, what happens is that the evanescent tail of the light in the upper waveguide can excite the lower waveguide. But if these waveguides are made of zero index material, you get strong coupling no matter how large the separation between the two waveguides is. So this is just another really strange consequence of working with Epsilon near zero materials. And finally, and I'll come back to this at the end of the talk, you have automatic phase matching of nonlinear optical processes. So just very schematically, let's think of the usual four-wave mixing process. If you have two input photons going in the forward direction, the two output photons also have to go in the forward direction to satisfy a phase matching process. But look, if the refractive index is 0, then K and omega over C is 0. That means you automatically get delta K equal to 0. So you can have very, very strange processes in which two input photons like this scatter through a nonlinear process so that one photon is going in the forward direction and one's going in the backward direction. And your first thought is, but that doesn't conserve momentum. But the answer is yes, that does conserve momentum, or at least crystal momentum, because the two input photons each have 0 momentum and the two output photons both have 0 momentum. Okay, so that was very, very rapid, but I have a lot of exciting things to tell you about. Let's move on to the next topic. This is nonlinear optical properties of these zero index materials. So, and now this is meant to be very, very schematic. In photonics, one is very interested in producing all optical switches. And just schematically, here's the interaction region. Here's an input beam, generates an output beam. Here you have a control beam. And the idea is that if the control beam is on, then you get output. If the control beam is off, then you thank goodness. If the control beam is on, then you get an output. If the control beam is off, then you don't get any output. So what properties do you want? Well, without going into the issues of the geometry, this has to be a nonlinear interaction because one beam of light is interacting with another beam of light. You want the nonlinear response to be very large because you want to switch this with a weak beam, and you want this to be very fast so that you can use it for even terabit per second switching. So you want a highly nonlinear material. And let's remind ourselves, how does one quantify the strength of a nonlinear response? And there are actually two different methods. One is to quote the N2 value of a material. Here, the refractive index in the presence of light of intensity I is given by the weak field refractive index plus N2 times I. Other way of describing nonlinear optics is in terms of the nonlinear susceptibility. This tells you how the polarization, the nonlinear polarization, dipole moment per unit volume, depends on the applied electric field strength. It's given by this equation here. So N2 and Chi3 are the two standard ways of measuring how strongly nonlinear a material is. So how are they related? Well, there's a very, very simple relation given in any textbook on nonlinear optics. N2 is given by Chi3, these combinations here, but the crucial point is that the refractive index and the real part of the refractive index appear in the denominator. So we can think of Chi3 as being the fundamental parameter. N2 depends on the geometry that you're using. So if we are working with a zero index material, we expect that N2 to be very, very large, very much enhanced compared to the usual circumstances. Okay. Okay, so how do you choose an epsilon near zero material? I hope I've conveyed the thought that, that there's some really interesting things you can do with epsilon near zero materials, but how do you go and get one? So first of all, you can use an electrical conductor. All conductors display ENZ behavior at their plasma frequency. And to remind you of this, metals are often described very well by the Drude formula, which is given here. Now, you can see by inspection that the real part of epsilon will vanish at a frequency given by the plasma frequency divided by the square root of epsilon infinity. Epsilon infinity being this constant out front. So this works well. Many demonstrations of epsilon near zero have made use of conductors, but this doesn't work at all wavelengths. You need to work at a wavelength in which you have a large number of free electrons. This can happen in the ultraviolet for many metals, or you can push this down into the near infrared by using a semiconductor. Now, what about electrical insulators or dielectrics? Clearly you don't have any Drude formula for a conductor, for an insulator, but dielectrics can show epsilon near zero behavior at their phonon resonance. This phonon resonance for known materials lie in a range in the mid-infrared. So both of these work very nicely, but each of them is limited in its wavelength response. You can use metamaterials. So the idea is that you find a clever collaborator to design a material that has epsilon near zero or even epsilon and mu near zero behavior at the wavelength of interest. Now, there's a challenge. For any of these three examples I've given, you want to have low loss. If you have high loss, then all your light gets absorbed and turned into heat. So to get low loss, you want the imaginary part of epsilon to be as small as possible at the wavelength at which the real part of epsilon vanishes. And this is a real challenge. And the material scientists who are working in this field, this is what they are fighting, trying to find situations in which you can minimize the loss of the epsilon near zero material. Now, the material that I have concentrated on in my own research is indium tin oxide, or ITO. Indium tin oxide, it's likely that everybody in the audience has a sample of indium tin oxide with them. The touch screen on a mobile phone is usually, maybe always, made with indium tin oxide. Indium tin oxide is it's a transmissive conductor of electricity. Now, what we discovered is that at its ENZ wavelength, ITO possesses a nonlinear coefficient that's maybe 100 times larger than any previously reported material. Well, what is ITO? It's a degenerate semiconductor, by which I mean it's so highly doped as to be metal-like. It has a reasonably large density of free electrons, leading to a bulk plasma frequency according to a wavelength of 1.24 microns. So this is where this is where most of my research is done, working at this wavelength here. We find that the dielectric properties of ITO are very well described by the Drude formula. Now, there are other transparent conducting oxides that also have strong nonlinear response at the ENZ wavelength. AZO, or aluminum doped zinc oxide, is one example of such a material. And this is the material that has been used by Shalaya, Voltaseva, Kaspani, and Faccio. Okay, so I said that we chose indium tin oxide as our preferred epsilon near zero material. This quad chart sort of summarizes 2 years of our research on this material. So first of all, we did ellipsometry on the material. And here is a plot of the real part of epsilon and the imaginary part of epsilon as a function of wavelength. And you see that the real part of epsilon vanishes at a wavelength of 1.24 microns. So we then took the sample and we measured the N2 coefficient. We did a Z-scan measurement, and we found that the N2 value is enormously large. So here is our measured value of N2 as a function of wavelength. This red arrow is pointing to this baseline here. N2 of ITO is so much larger than that of other materials that chalcogenide glass doesn't even show up in the same scale. Now, what is maybe truly remarkable is that the overall change in refractive index is almost of the order of unity. Now, four-wave mixing by nonlinear optics, oftentimes we're talking about refractive index changes that are a part in 10 to the fourth. Most materials simply don't give you this much of a refractive index change, but indium tin oxide does. So, and we did this by measuring the real part of N as a function of intensity and the imaginary part of N as a function of intensity. And lastly, if you want this to be a good switching material, you need it to be fast. So we did pump probe experiments, and we found that the turn-on time is 200 femtoseconds, and the relaxation time is something like 360 femtoseconds. So this is all sub-picosecond response. The material itself will support a terabit per second switching rates. My apologies, my voice is going away, but I will fight on. Now, it turns out that the nonlinear response of ITO is larger for oblique incidence. Here's a very simple calculation. And for right now, we'll just ignore the reflected part. We want to ask, what is the electric field inside the material? How is that related to the incident field? So of course, the boundary conditions are that the parallel parts of E are continuous and the perpendicular parts of D are continuous. Put these two relations together. It tells you that the field inside the material is related to the incident field in this manner here. So you can see that if epsilon is less than 1, there will be angles at which the field in the material exceeds that of the applied field. So we tested this out as well. So here we did more Z-scan measurements. We measured N2 as a function of wavelength, but for a variety of angles of incidence. So we just took our sample and rotated it within the beam. This is the maximum value we saw. Over here, we plot the N2 value as a function of angle of incidence, and we see that it's going up at 60 degrees. We're unable to reliably do any measurements at larger than 60 degrees because there was so much surface reflectivity that we did not have a strong enough signal to measure. So, question, why is N2 so large for indium tin oxide? I'm claiming it's the largest nonlinearity ever measured. Well, first of all, ITO is pretty nonlinear to begin with. So if you, away from the ENZ resonance, let me remind you, in the wings here, in the distant wings, this we measured N2 at those wavelengths, and we found that it is well, has this value here, which is 150 times larger than that of fused silica. Now, there's an enhancement. There's a 43 times enhancement from working at the ENZ wavelength, and there's an additional 43 times enhancement from using non-normal incidence. Complete coincidence that these two numbers turn out to be the same. You put all this together, you find that N2 is 0.01 centimeters squared per gigawatt, and this is 300,000 times larger than that of fused silica. Now, here I ask, why is N2 so large for indium tin oxide? Now I'm going to ask the question from a more global point of view and ask, why is it that epsilon near 0 conditions lead to a large nonlinear optical response? And there's maybe 4 different ways that we can understand this result. But first of all, this is what I've talked about already. N2 is related to chi3 by having these values of n in the denominator. So when n is very small, N2 is very large. Now we can state that more generally. Let's say that the refractive index is a background value plus delta n. Let's say that epsilon is some background value plus delta epsilon. And we want to know n. So it's the square root of epsilon, which is the square root of epsilon back plus delta epsilon. I will not go through the math. You know how to do this. But what you find is that the change in refractive index is given by the change in dielectric permittivity divided by twice n of the background. So when the background index is very small, you get a much larger change in refractive index for a given change in epsilon. You can also see this. You can sort of feel why this is important. Let's look at the wave equation and let's look at the behavior when epsilon is equal to 0. So when epsilon is equal to 0, this term disappears entirely. The nonlinear response is no longer a perturbation to the linear response. The nonlinear response is the totality of the response of the system. And finally, start with Maxwell's equations and just manipulate them a little bit. We can take this as a measure of the nonlinearity, how rapidly the field changes spatially divided by the field itself. We find that this quantity is proportional to the square root of mu over epsilon. So we want epsilon near 0, and we want mu to be as large as possible. And detailed numerical integration confirms this result. And here are our results. This work is done jointly with a group of Nader and Gata. So almost as simple a problem as you can imagine. we solve the standard equations for second harmonic generation. So here, the rate of change of the second harmonic field is given by chi2 times the square of the fundamental applied field. And of course, this acts back on the fundamental applied field at the incident frequency. And this one is driven by chi2 times A2 times A1 star, times A1 star. Now, just for simplicity, let's assume we have perfect phase matching, and let's plot the efficiency for various values of epsilon. So here is the intensity of the second harmonic generation, plotted as a function of Z as the light propagates through the material. This curve is for epsilon equals 1. Now, when epsilon is 0.1 or 0.01, you see that the growth rate of the harmonic field is very much faster. So in some ways, epsilon near 0 is no longer that mysterious. You can see it just pops out of the basic equations of nonlinear optics. Okay, so let me move on with the talk. So we have a very strongly nonlinear material. What we want to do is do useful things with it. So one thing we've done is to place an array of nano antennas, gold nano antennas, on top of the ITO. So this is the concept here. This is the actual SEM photograph of the surface that we made. So when we put these antennas on top of the ITO, we expect we expect the nonlinear response to be enhanced, and there's two separate reasons why it's enhanced. First is the simple lightning rod effect. When you put an antenna here, it will concentrate the electric field into the region of ITO immediately below it. And second of all, we have coupled resonators. We have the ENZ resonance, and we have the resonance of the antennas themselves. If we put these two resonances on top of one another, we get an even larger enhancement of the nonlinear response. And just to see this here, this is a plot. It's called the dispersion relation of an epsilon near 0 material. It's a plot of the frequency of light against the wave vector of the light. To calibrate ourselves, this is the light line in the vacuum, where K is omega C over N. This is the light line for BK7, a standard optical glass. But here are the two surface plasmon modes of indium tin oxide. This one is called the long range SPP mode. It's almost independent of wave vector. And this is the short range SPP mode. And this is the one that maybe most of us are more familiar with. And this does act as a function of wavelength. Okay, so we fabricated this sample. We measured N2 as a function of wavelength. This is the results that we had. The red is the simulation, which is a good but clearly not a perfect fit. There's some things to notice here. First of all, the N2 value is even larger now. It's something like 20 million times larger than that of silica. The other thing you note is that the N2 value can be either negative or positive. That can be useful. I mean, usually we want a positive N2, but there are times we want a negative N2. And this system can give you either positive or negative. Also, the wavelength at which we switch from a positive value to a negative value, we can control that. by changing the length of the antennas, or more generally by changing the dimensions of whatever antenna we use. We can change this crossover point. So N2, if we're talking about superlatives, N2 is 7 orders of magnitude larger than that of silica glass. Okay, let's quickly then talk about materials for ENZ and then move on. So I'm not going to go through this slide. This slide simply is a reminder that there are a lot of people in the world who are excited about epsilon near zero and near zero index materials. And here's a brief summary of some of the people who've worked on this. Now, in the US, I am part of a DARPA project, and my other team members are Nader Ngeta, Eric Mazur, and Alan Wilner. These are well-known names. So we decided to put our heads together and work jointly on developing both better ENZ materials and developing applications of these ENZ materials. So everything I tell you from here on, it will be a collaboration among some combination of the four of us. So first of all, what material systems are we working on? Well, I've already told you about this. So this is the Rochester effort. It's the nano antennas on an ENZ substrate. At Harvard University, Eric Mazur is working on Dirac cone metamaterials. And this is too complicated to explain in a few minutes. I'll just tell you that he's doing this. And Nader Ngeta at the University of Pennsylvania is working on what he calls photonically doped metamaterials. So here in 2 dimensions, you put a dielectric rod inside of what is otherwise an epsilon equals 0 material, and you find that there's some very unusual, you can induce a magnetic response and potentially a very large nonlinear response as well. So these are things we are working on. Let me just tell you a little bit about the Dirac cone metamaterials. This again is the Harvard group. This is actually an epsilon and mu near 0 material. It's called a Dirac cone because if you plot the dispersion relation, you find that instead of being a parabola, this looks like a cone, and this surface and this surface meet at a point. So here are the measured values of the refractive index as a function of wavelength. Here's the real part of the refractive index, and you see it passes uniformly through 0. And but here is the real part of the surface impedance. And you see that the surface impedance does not go to 0, neither does it become infinite at this point here. So they're able to get light into the material, and there's a very large nonlinear response at the epsilon near 0 point. Well, here are some of their results. So they've built a waveguide within their Dirac cone metamaterial. But for the waveguide itself, they can drill simple holes in it by lithography, of course. They can place holes in it. They can make a very, very thick layer, and they can make a symmetry protected 0 index material. Now, the point of their study is that they want the Q factor of the resonance to be as large as possible, the quality factor, or Q. The reason is that the larger the Q factor is, the longer the light will stay around and the larger the nonlinear response. So they're able to get 0 refractive index in all of these structures, but they get a very, very large Q factor for this structure here. What they mean by symmetry protected is that atoms within this waveguide cannot radiate. It's a non-radiating current distribution. So you see there's a progression of getting the Q factor larger and larger as we go through the sequence. Oh, and we're running low on time. Let me just move on to this. So this is within my own group. We've measured the nonlinear optical properties of a layered metamaterial. So why did we do this? Well, first, what do I mean by layered metamaterial? It's a stack of metal dielectric, metal dielectric, metal dielectric. So first of all, this is a metamaterial. The previous work that I showed you was all because of a surface plasmon resonance. We want to establish that layered, that metamaterials also show epsilon near zero behavior. And enhanced nonlinear optics at their zero index point. So here we plot the dielectric permittivity as a function of wavelength for various values of the ratio of the metal to the dielectric content in this material. And what you see is that we can choose the epsilon near zero wavelength to be anything we want in this range of 300 to 700 nanometers. We decided to work at 508 nanometers. It's a convenient wavelength to work at. So we designed a system to do this. It's 16 nanometers of silver, 65 nanometers of silica, and 5 layer pairs of them. And you see that the real part of epsilon does vanish at 508 nanometers. We've measured the nonlinear response using what's called the Z-scan method. I won't go into the detailed analysis. I think what's cleaner is just to look by eye. This is the response of silver. This is the response of the composite material. And the composite material is much larger than that of the silver. So the answer is yes. Layered metamaterials do show enhanced nonlinear optical response. And finally, in the time that's left, let me talk about some of the applications of ENZ materials. So first of all, we're interested in something called time refraction. Do I have the right? No, I skipped one. Okay, we're interested in adiabatic wavelength conversion through a process known as time refraction. So let me remind you that usually when we talk about refraction, we're in the spatial domain. Here a beam of light passes through the interface between a region of index N1 and a region of N2. And what we find, of course, is that the frequency of the light is the same in both materials, but the wavelength of the light changes in entering this material. Now, in the time domain, we can talk about time refraction, an analog of Snell's law. Here, as a function of time, at time t equals 0, we suddenly change the refractive index of the material. And when we do things this way, the wavelength remains constant, but the frequency changes. A time rate of change of the refractive index is going to change the frequency of any light that's inside the material. So this is called time refraction, and it's potentially useful. Yes, we have optical parametric amplifiers, but this is a much simpler way of shifting the wavelength of light. Now, time refraction is very closely related to the process known as self-phase modulation. Self-phase modulation says that the frequency changes by an amount. That's the time rate of change of the nonlinear phase shift, which is the time rate of change of N2 times I times omega over C. So if the intensity is changing in the function of time, you do get a change in the frequency of the light. So how did we study this? Well, in the laboratory, we have an OPA, produces a pump beam and a probe beam. We have a delay line here that can control when the pump pulse falls on the sample in relation to when the probe pulse falls onto the sample. And then we just take the transmitted probe beam and look at its spectrum using an optical spectrum analyzer. And here are some of our results: experiments, simulation, very close. Here you see that as we change the time delay of the pump pulse with respect to the probe, we can get either a positive change in frequency or a negative change in frequency. And here we summarize a whole sequence of measurements of this sort. Here, as we increase the intensity of the pump beam, the blue shift increases when we're on this side, or if we choose to be on this side here, we get a red shift, and we see that the red shift increases as we increase the intensity of the beam. Now, is this important? Well, look, we are seeing frequent wavelength shifts of the order of 80 nanometers, and that is enough. That is enough to lead to applications in wavelength division multiplexing for telecommunication. Okay, I told you about this before, but here are the results. Relaxed phase matching requirements in an ENZ material. Here was the actual study. We studied a four-wave mixing process where two pump photons turn into a signal photon and an idler photon. And the key result is that we find that an idler field is generated in both the forward and the backward direction. So here is the data. We've already talked about this. In the forward direction, we get the usual type of forward four-wave mixing. But what is very, very unusual here is that we can also see phase matching in the backward direction. Now, why is this important? Well, it says that nonlinear optical processes that previously were believed to be too weak to be studied can be excited using ENZ materials. So if you're working with ENZ materials, this phase matching requirement is something that is automatically satisfied. And let me ask the organizers, when did you want me to stop?
You can go for another 10 minutes.
Okay, good. Within 5 or 10 minutes, I'll be done anyway. So,
Yeah.
so that's perfect. I forgot to ask you before the talk started. Let's skip this. That's right before a different talk. Okay, real-time holography with terahertz refresh rates. I like to motivate this by looking at this frame from the first Star Wars movie. And here we have a holographic image of Princess Leia talking to Obi-Wan Kenobi. But the point I want to make is that in 2021, we still do not have holographic materials that can support video frame rates. We don't know how to do this today. So our goal was to do real-time holography with video or even much faster refresh rates. I remind you that ITO has an ultra-fast response that permits terahertz refresh rates. And well, it leads to important applications. Princess Leia is just one type of application, but holographic methods are also used for correlation, convolution, other types of data processing. So, we set out to do this. Maybe let's look down here. This is the actual experimental configuration. So for the input, we have a reference beam and a signal beam. This happens to be an OAM pedal beam, but the idea was just to have some structure here so we could see what's happening. So we allow these two of them to interfere with one another. They create a grating on the indium tin oxide. Then we send in a readout beam, and we get a reconstruction of the signal beam. We also get the conjugate of the signal beam. So this is a standard holographic setup, but all the interaction is taking a sub-picosecond rate. Remember, this grating will disappear 1 picosecond after the pump wave leaves the material. And we get good results here. And just as a demonstration of image processing, we show that we can do edge enhancement using the holographic method of the indium tin oxide. So I guess I am done. So, but summary, let me tell you what I think are the important things about ENZ materials. Well, extremely interesting physical processes can occur in ENZ materials, and this has certainly not been exhausted. There's still plenty of important experiments to be done. Second is that ENZ materials display extremely large nonlinear optical response. And this huge ultrafast nonlinear optical response of ENZ materials can lend themselves to many important applications. Let me remind you what I said at the beginning. The visuals for this talk are posted at my website. This is easy to remember, boydnlo.ca. And let me just then thank all my students. I have a research group both in Ottawa and Rochester. And the students who are part of the two groups are just incredible. And they're responsible for all the work that I've showed you today. And I won't go heavy on this, but we love Indian graduate students. So if anybody in the audience is interested, please think of coming to either Ottawa or to Rochester. So I thank you for your attention, and I'm done now. I'd be very happy to answer questions.
So, dear Professor Robert Boyd, thank you so much for being part of our Silver Jubilee celebrations and for giving a wonderful talk on ENZ materials and their applications. So it was amazing, and we really enjoyed the talk. We are so honored to have the opportunity to listen to you today. Now, if you may permit, I shall read the questions that has been posted on the Q&A, just for easiness. And let me read one question. Does ENZ materials or metamaterials exhibit temperature-dependent refractive index? Any comments on that?
Oh, yes. I mean, if you look carefully enough, everything has a temperature dependence. We have not encountered any really strong temperature dependence in anything we've done. Of course, in the back of our minds, there are these phase change materials in which you can drive a structural phase transition by adding just a little bit of heat into the material. We haven't done that yet, but that sounds very intriguing, and we might want to do that soon.
Sure. Okay. Another question is, what makes ITO so special among the category of TCOs? Can we expect similar results for other TCOs as well?
So my answer is yes. We can expect we can expect the other TCOs to behave similarly. Aluminum doped zinc oxide, I gave that example during the talk, is another material that shows a strong nonlinear response. I guess when 5 years ago, when I started this effort, the first step, I didn't care that I had the world's best ENZ nonlinear material. I wanted to demonstrate that ENZ material was showing nonlinear response. I went through tables of optical constants, and I convinced myself that indium tin oxide would work. So that's how we got on indium tin oxide. There are probably many others.
Is it possible to use noble metals instead of ITO?
Sure. I expect that would work very well. The noble metals have their plasma frequencies in the ultraviolet. But sure. we have lasers that work in the ultraviolet, but I doubt that we would be wanting to use ultraviolet for photonics, for optical logic or communication. Of course, the higher the carrier frequency, the larger the modulation rate you can use. But I think we're thinking really in the future where one would want to use ultraviolet light for transferring information over large distances.
Okay, so maybe a last question. In ENZ materials with a considerable value of mu, will it be possible to model giant NLO properties with an applied magnetic field, maybe?
Oh, that's a very good question, and my answer is it's well worth looking into. It's well worth looking into. I just have not looked into that yet, but it's something I would like to do.
Okay, and then thank you very much for answering our questions. And now I hand over the session to our director to conclude the seminar. Over to you, Pramod sir.
Professor Bob, that was an excellent talk. Thank you for joining us to give this seminar, a talk in our seminar series. We had an excellent overview of the applications of ENZ materials. I thank you on behalf of all the members of the organizing committee and especially the entire International School of Photonics for giving such a wonderful talk. Thank you, Professor Boyd.
Thank you for those kind words. Thank you for those kind words. I hope we get to meet in person one of these days when the coronavirus is over. But this is, I guess, Zoom is as best we can hope for now.
I think we'll keep in touch.
Very good. Goodbye, everybody.
Good day. Good day.
Goodbye.